and thank you for your patience. So I'd like to introduce our speaker, Carmel Majidi. He's an assistant professor of mechanical engineering at Carnegie Mellon University, where he leads the soft machines lab. And I've been told that he has 2 Maryland graduates in the soft machines lab. So Carmel was a postdoc at Harvard with Rob Wood, George Whitesides. He was also a postdoctoral fellow at the Princeton Institute for the Science and Technology of Materials with David Shrolovitz and Miko Hatia. So he got his PhD at Berkeley, where he worked with Ron Faring and Bob Full, looking at gecko adhesion and shear activated adhesion. And he's one of the few people I can say who's won the Grand Slam of Young Investigator prizes from DARPA, ONR, AFOSR, and NASA for soft robotics research. So please join me in welcoming our speaker.
Thanks a lot, and it's a delight to be here. Am I fine? I don't have a mic on me, but will it be okay for the recording?
Yeah, that's fine.
Okay, great. So I'm going to share mostly highlights from the past year from my research group, Soft Machines Lab at Carnegie Mellon. And I do also want to kind of take this opportunity to kind of target in or kind of focus on a special class of problems that we've most recently been looking at and focusing on how lessons from mechanics, and in particular finite elasticity, and mechanics of large elastic deformations can help inform some of the efforts here. But the overall theme is to use mechanics, insights from mechanics, to develop new classes of soft multifunctional materials that would make robots a little bit more friendly. Okay, so robots, I mean, there's been this, for decades, this promise that we would have service robots that we could bring into our homes. These would be fairly affordable. Every family could own one. But when it comes to kind of what we have existing in terms of conventional robotics, I mean, an idea like this is something like this would be terrifying, right? For the most part, I mean, yeah, robotics has not delivered on this promise of service robots, but it certainly has done extraordinary things in an industrial workspace. Okay, so the idea here is, what do we need to do engineering-wise to get from this to something like this, right? Where we could have robots in our homes, hospitals, schools, and kind of from a mechanics perspective, what I see is a really kind of big challenge, and this is kind of not just from a robotics and application standpoint, but more of even a scientific or intellectual challenge, is how do we kind of re-engineer our robots and machines using a completely different set of materials, and in particular, materials that are on a completely different end of the spectrum when it comes to Young's modulus. Okay, so Young's modulus is just kind of one metric, one measure of the elastic rigidity of a material, and even for Young's modulus, we know that this is a fairly limited definition, right? I mean, Young's modulus scales with the amount of force it takes to stretch a material, and it's fairly linear when it comes to very small strains, strains in the order of, say, fractions of a percent. But when we're talking about soft robotics or soft biologically inspired type machines and systems, it's quite possible that we're going to be seeing strains well outside of this linearized regime where Hooke's law is applicable, right? So we have to kind of be a little bit kind of more careful about the types of constitutive properties and the theories that we use to examine these classes of materials and machines. Okay, so Hooke's law is fine for kind of conventional, more rigid materials, hard plastics, metals. But a lot of the work that we do in my lab is in addition to kind of re-examining the materials that we use, we also kind of re-examine a lot of the scaling laws and the design principles, and that's based on these non-linear constitutive relationships that we see are most relevant for these kind of elastically soft and highly deformable type systems. Okay, so that's kind of one element of it. Another element that I'm not going to talk quite as much about is rheology. Okay, so in addition to kind of going to elastically soft materials, we're also going to increasingly use fluids in a lot of our electromechanical systems. And so even in that case, I mean, if you have Hooke's law, we have to account also for the viscosity and some of the kind of almost fluidic type responses of these materials. And just kind of a crude type of representation of this would be, say, a Kelvin-Voigt law, which actually does a fairly good job of at least the first order representing viscous effects in elastic solids like rubber. But I think, kind of increasingly we have to challenge ourselves and think about even kind of more exotic types of materials and, things like magneto-rheological fluid, electro-rheological fluid. Materials that have been, popular to some extent in automotives and aerospace, and start kind of applying them also to the space of soft robotics. And so electro-rheological fluid, I think, is kind of one very promising type candidate. So fluid that has very low viscosity naturally, but then when you apply very high electric fields, so when this goes in, these two probes, when we apply, say, like a kilovolt drop between them, suddenly this liquid is going to go from having a fairly low viscosity, having such a high viscosity, you could treat it almost like a solid, what's called a bingham plastic with some kind of measurable shear yield strength. And then instantaneously when we move the field, it goes back to being fluid. Okay, so these are kind of generally the classes of the materials that we're looking at. Okay, so soft, elastomers, silicones, urethanes, liquids like electromagneto-rheological fluid. If we want to introduce, say, electronic functionality into these elastic materials, I mean, kind of a very mature technique, and some of you guys are doing this, is to put some type of conductive fillers or to tune the insulating properties. You could say put like barium titanate or something in there, right? So that's one way to introduce electronic functionality in these soft materials. Another approach is actually to integrate networks of microfluidic channels of conductive fluid. Okay, and one material that we use in particular, and I'll kind of, towards the second half of this talk, I'll talk about some of our efforts and fabrication techniques or rapid rotating techniques using these what I call liquid phase metal alloys. So these would be like Gallium-Indium type alloys that are liquid at room temperature, but are just as conductive as any kind of conventional metal wiring. And then other materials that some of you guys probably are familiar with, shape memory alloys, nitinol, and then there's gels, hydrogels, aerogels. Increasingly we're kind of doing work in that space as well. Okay, so if you allow me or kind of indulge me in making kind of one sweeping pronouncement, I would kind of categorize kind of all these types of materials as falling under this category of kind of soft matter engineering. This is, I understand, an abuse of terminology, because the physicist soft matter means something very specific, related to gels and then colloids and emulsions and things like that. Here I'm kind of making a kind of a much broader kind of admitting a much broader kind of range of materials here when I talk about soft matter engineering. But really, kind of the attitude is that we're using entirely materials that doesn't introduce any rigidity into our system, and by rigidity I mean any kind of material that has a Young's modulus or a composite with an effective Young's modulus of a megapascal or more. So we're exclusively dealing with materials that have a lot of the same elastic and rheological properties of natural biological tissue. So pretty much everything except for bone. Okay? So just in perspective, like your skin would be on the order of a few hundred kilopascals up to, if it's dry, maybe like a megapascal. And then any kind of the fatty type tissue or muscle tissue, nervous tissue. A lot of that other biological tissue kind of ranges from on the order of kilopascals to tens or hundreds of kilopascals. So that's kind of, if you would indulge me, that's kind of what I'm calling soft matter engineering. So can you make electronics, actuators, multifunctional materials, transducer exclusively with this class of materials? And so I'm going to focus on efforts with actuation, so basically like kind of like a soft artificial muscle for these robotic systems, soft stretchable electronics and circuits. And then, as I said, kind of the last kind of half of this talk, I'll kind of focus, or maybe the last third of the talk, I'll focus on sort of fabrication techniques. Sounds good? Okay. So actuation. So soft robotics, this idea that you want robots that are not driven by bulky, heavy kind of hardware. This has been around for quite a while, okay? And I would say kind of the earliest soft robots use pneumatics, and then these are based on kind of what's now called the McKibben actuator, okay? So this is, again, something that I would expect a lot of you guys are familiar with. Basically, we're just, controlling the kind of air pressure inside our elastic cylinder, and we have some kind of a weave here of inaccessible fibers that introduces some kinematic coupling between contraction and diameter, and we have control not just on length, okay, so we don't just have shape control, we also have reversible rigidity tuning here. And they're coupled together in a way that we can kind of overcome this almost paradox of soft robotics, which is, how do you have soft materials become load-bearing and capable of doing mechanical work? Well, one way to do it is with pressurized air, and there's been quite a lot of success over the decades, not in terms of commercial implementation, but at least at the level of kind of like prototypes, in terms of looking at this for, say, a soft robot arm, for example. So this is a project at Hitachi. And then also, actually, McKibben himself was a biomechanician. So actually, the idea for this was actually from Moran back in the 1940s, and then McKibben adapted this for basically wearable exoskeletons in the late 1940s and 50s. His idea was to kind of use that for human motor assistance. So one of the kind of the more recent advancements is taking some of these kind of paradigms, maybe is a loaded word, but like architectures in pneumatics and combining that with recent advancements in rapid prototyping, in soft lithography manufacturing, to make soft inflatable robots, even all the way down to the micro scale. So work that probably a lot of you guys are familiar with from George Whiteside's group. Probably you're less familiar with the work that had been going on for the previous few decades out of Koichi Suzumori's group at Okayama University, using a lot of these same kind of pneumatic type architectures. So that's very exciting. It's not quite the kind of work that we do, but I think kind of a very exciting kind of complementary type approach to soft robotics. Another approach, and this has kind of been mixed interest, depending on what your application is to use shade memory alloy and using kind of more kind of thermally responsive type materials. And this is kind of I would say a very quick and easy way to make kind of soft robot limbs, and so this would be a good alternative to say using motors, but there are certain fundamental limitations in terms of power efficiency. I mean, these are very power hungry. I mean, we're talking energy input to mechanical work output efficiencies that kind of max up around 5%. They get very hot, so not necessarily appropriate for contact with human tissue, let alone internal organs, and also fairly slow. And these are kind of mock-ups that some students and I made for the soft robotics class that I teach at CMU. But nonetheless, a kind of a very kind of simple and versatile way of if you kind of want to have a, say, soft robot made in an afternoon, you can use shade memory alloys. Kind of, in terms of my own kind of study and research, I've kind of converged on dielectric elastomer actuators, and this has been around for quite a while as well, about 2 decades. A lot of pioneering work out of SRI on dielectric elastomer actuators and integrating them into these kind of, I guess these would be kind of also prototype or early versions of soft robots. The principle here is actually very straightforward. I mean, if you have, and for those of you who are not familiar with dielectric elastomer actuators, basically we're taking a rubber sheet, some insulating film, and then we're just coating the 2 sides of it with a conductive fluid. Okay, so it could be just like carbon powder or carbon grease. It could be or it could be like say, say in Sarah Bergman's group, for example, where they use conductive elastomers. We use that liquid metal alloy that I talked about. You coat both sides with it, and when you apply, regardless of what the conductive medium is, once when you apply electric field, basically you get charge buildup, equal and opposite charge on the 2 sides of this insulating elastic film, and then those electrostatic forces basically squeeze that rubber, and they cause the thickness to reduce, and because the rubber is incompressible, it causes the planar area to expand. And depending on what kind of kinematic constraints you introduce, you can kind of use this for like linear actuators, you can use this for bending actuators, and so it's fairly kind of versatile in that respect. One limitation, though, is the very high amounts of electric field that's required to kind of actuate this. Okay, and so kind of one term for this is what are called the Maxwell stresses that are internally induced when you apply that very large electric field. And kind of one technique, and I do think it's worthwhile to kind of get into the underlying mechanics and math a little bit. I understand it's a good Friday afternoon, and but I just kind of quickly will go through the derivations. I'm not going to explain every single variable here. I just do want to highlight the point is that classes of materials like this, they adhere to, or these classes of materials adhere to classical theories in solid mechanics, in finite elasticity. They adhere to Maxwell's equations. Okay, there's nothing kind of new or fancy or exotic that we're introducing. Okay, so we should be able to use kind of reliable and familiar engineering techniques in order to come up with scaling laws and design rules for dealing with these types of actuators and materials. Okay, so one approach that we make very heavy use of in my lab and even in the class I teach, the soft robotics class, is this Rayleigh-Ritz approach, right? Where we just basically accumulate all the different contributions to potential energy in our system, and then we find a configuration at static equilibrium that minimizes the total potential energy. Okay, so in this case, one source of potential energy, of course, is the elastic strain energy. Okay, and we can use any kind of a nonlinear constitutive model to represent what that stored strain energy is. I mean, just kind of here, I found that for these materials, a fourth order Ogden model is the most relevant because it exhibits this kind of strain stiffening effect when we go to much larger stretches. Okay, so that's one contribution. The other is the electrical enthalpy, okay, associated with all the electrostatic charge on these two surfaces. So we add them up, take the total potential energy, we minimize with respect to our free variable, which in this case is the thickness, and then we get our scaling relationship between thickness and applied voltage, okay? And we can go ahead and plot that, and what we find is something somewhat unsettling. Okay, what we find is that, and I've kind of normalized voltage here with respect to different parameters like thickness and shear modulus of the solid and its electric permittivity. Regardless of kind of how you want to show this curve, the bottom line is that you apply all this voltage, kilovolts, okay? Like, 1 kilovolt, 2 kilovolt, nothing happens. And then suddenly you apply, say, 3 kilovolts, suddenly you see a little bit of change in thickness. And then you go to, like, say, 4 kilovolts, okay? And then you get this instability, okay? This electromechanical instability, where suddenly you go from having basically no actuation, no response, to suddenly complete collapse and failure, okay? And this is kind of catastrophic failure in the sense that you can't use your actuator after you've undergone this instability. In fact, before you even reach this instability, what typically happens is that the voltages will be so high that you'll get either electrical arcing around the insulator, or you're going to get dielectric breakdown through the insulator. Okay, and so just to kind of demonstrate that, again, this is kind of a demo for the soft robotics class, but this is the dielectric elastomer actuator, where I've basically has some natural bending curvature due to that kind of pre-stretch of the dielectric film. I apply 2 kilovolts, you get very modest deflection, okay? I apply 3 kilovolts, a little bit more, okay, so that's kind of promising. But now when I go to 4 kilovolts, you'll see what happens, okay? So when I go to 4 kilovolts, now I'm getting very large deflections, okay? But then I get, you saw that spark there, I got that dielectric breakdown, okay? And basically I fried this actuator at this point, okay? So the kind of lesson here is that when it comes to using these materials, they have a lot of great advantages in terms of the simplicity of fabrication, in terms of their incredibly high efficiency, okay, their low power requirement, the potential for very high speed. Okay, I kind of intentionally kind of look at this slowly, right? There's all these advantages, but one disadvantage, right, is that we have very little margin for error. Okay, if I apply too little voltage, I don't get kind of much response. If I apply too much, I have this. There's always this running this danger of failure. Okay, so as an engineer, I shouldn't be scared. Okay, I should just basically kind of enter this kind of being informed with good quantitative predictions that kind of tell me what is that appropriate window of operation. Okay, how much voltage is too much voltage, and kind of what is that threshold of voltage for me to start seeing kind of enough deflections that this could be kind of do something useful, say, for a soft autonomous field robot. Okay, so that's kind of where the theory and predictive modeling comes in. Okay, so I hope that this is kind of what I want to motivate for the kind of the next few slides here. We're actually going to kind of go and look at this a little bit more carefully. Okay, so what is a good theory for these bending actuators? So basically, what I'm doing is taking my dielectric film, I'm coating two sides with my conductive fluid, I'm pre-stretching it, bonding it to this kind of this additional layer, okay? And then when I bond these and let go, as you'd expect, because of the residual stresses in this pre-stretched layer, this thing is going to curl upward, okay? So hopefully you have that intuition. And so we fabricate these, and something like this, if you just assume kind of planar, kind of a circular type arc during bending, we can again use our Rayleigh-Ritz technique and calculate what the elastic strain energy is just due to that pure bending. We can balance that with the electrical enthalpy. We get our total expression for potential energy, minimize it with respect to bending curvature, and we get this dashed curve that is in fairly poor agreement with our experimental results. Okay, so we did everything right in terms of, we know what material is, we know what all the dimensions are, we know what the electric permittivity is, shear modulus, all that. We're using just a classical plate bending model. This is also kind of captured by a Stoney's formula, and we're just way off when it comes to agreement between theory and experiment. Fine, we're kind of in the same general ballpark in terms of angle of deflection and then kind of the voltages at which we'll see responses. So it's good in terms of kind of getting kind of ballpark, but it's not a good theory in terms of actual operation, okay? And telling us kind of what is that kind of critical voltage that we have to avoid, okay? So if we want to be more accurate and we really want a predictive model, then we have to be very kind of deliberate and a little bit more careful with our kinematics, okay? So it was probably clear, maybe it was clear from the other pictures, but kind of if you look at these, the actual stable geometry of these dielectric elastomers carefully, you'll find that instead of just undergoing pure bending, it's actually undergoing this shell-like deformation where we have negative Gaussian curvature. We have two principal curvatures, one along this principal bending axis, but along the width, we also have some slight amount of bending curvature, but in the opposite direction. Okay, and so that's, kind of the first pass will be just to ignore that second principal curvature, except it turns out that that second principal curvature can potentially have a very big role in terms of establishing that electromechanical coupling between applied voltage and bending curvature. And what's actually kind of nice and a relief is that a lot of the same kind of mechanics, a lot of those principles using Rayleigh-Ritz technique, these variational techniques, they all still apply even for an elastic shell, okay? The challenge now is purely kinematics, okay? How do we represent deformation of a shell? And so there's, a few different ways we can do this. I just kind of, to me, I kind of came up with one way of kind of representing basically the position of points through the thickness of our shell as a function of these two principal bending curvatures. We can, take the gradient of that deformation mapping. We get our deformation gradient. From that, we get the principal stretches. We take the principal stretches, plug them in to our considerate model for Ogden solid. Actually, in this case, I used a Hookean solid. And then we kind of take the volume integral of that. We now add the electrical enthalpy. We take that total potential energy, and then we just minimize with respect to all our kinematic parameters. Okay, in this case, the bending curvatures and the corresponding arc lengths. And when we do that, we actually get an analytic solution now that is much stronger agreement with our theoretical predictions. And what's kind of important about this is we don't do any data fitting. Okay, this experimental prediction, it's not exact, it's not perfect. Even a shell model, there were certain types of simplifications that we were making just to make the problem more tractable. But the important kind of lesson here, or the thing here, is that just what we know about the dimensions during fabrication, based on what we know about the electric permittivity of these elastomers and independent measurements of the shear modulus, we can make these kind of open-ended, or not open-ended, but a priori predictions about what this coupling is going to be, and it's in much better agreement with our experimental results. And so this kind of does give us encouragement, that still principles of Maxwell's equations, variational techniques, finite elasticity all still apply to these classes of materials. And so kind of where this is going next and is to kind of look at other types of modes, right? So that was just kind of one type of dielectric elastomer actuator. We could alternatively kind of make a dielectric elastomer actuator with this kind of architecture where we have kind of alternating electrodes and dielectric layers, okay? And what's kind of interesting about this is not only will this function as an actuator, you could also use this as a transducer, say for stretch sensing, pressure sensing, also potentially as a generator for energy harvesting, okay? And so to kind of get a sense of that, and I'm going to kind of quickly kind of go through this because this is kind of more kind of the future direction we would like to go at with these classes of materials. But if you could imagine, say, having the cylinder, right, with alternating conductive and insulating elastomers. Basically, you have this kind of array, this series of capacitors, and if you say were to put this on some type of like aerospace structure, or some building where you get vibrations, you would expect to see changes in the capacitance of each one of these capacitive elements. So you get, say, if you kind of apply some harmonic excitation to this through your building, you get displacement at the base. That corresponds to 90-degree out-of-phase strains in each one of these capacitive elements. And then we can calculate what the corresponding changes in capacitance are. Now, I mean, there's kind of two modes of operation. Well, one thing we could do is, as this as we apply this harmonic oscillation, okay, as we kind of excite this, and we kind of get these periodic kind of compression in these capacitive elements, what we could do is kind of at those moments where there's compression, we could amplify that compression by applying electric voltage, okay? So in addition to all the inertial forces that are leading to compression, we also now have the addition of those Maxwell stresses, okay? And that's going to lead to amplification and kind of the even larger kind of amplitude here at the tip. So that would be an actuator type mode, okay? Alternatively, what we could do is, as it's stretching, that's when we apply electrostatic loading to the capacitors, okay? So basically, we're applying this kind of compressive stress to kind of resist or counteract that kind of tensile motion, that elongation. And in that mode, we're basically kind of introducing electrostatic damping. But that damping energy has to go somewhere. And that damping energy is going into the voltage stored in those charges inside those capacitive elements. Okay, and then we can take that those charges with that kind of heightened voltage and then extract that energy as electrostatic energy. Okay, so in that mode, we can kind of use this for energy harvesting, and then we can go and do free body diagrams, and we can derive the kind of governing PDEs. I'm kind of using a shorthand, kind of Einstein type notation here with how we represent the PDEs, and we have all our boundary conditions. We can pretty much plug in whatever strain energy density here that we want. Now, we could go linearize this, okay, and when we do, we actually get a closed form solution to this PDE, and that solution is helpful insofar as it gives us some kind of scaling law and some kind of general kind of ballpark estimate for how much electrical power we can harvest as a function of all the different kind of parameters, including the kind of the vibrational or excitation frequency. Okay, but if we do the linearization, there's a lot of things that we miss. Okay, because it turns out that we can, if we want to get kind of the most power out of this, we really have to kind of operate it in a regime where we're getting very large elastic deformations, okay? Because large elastic deformations will lead to those large changes in capacitance, and large changes in capacitance lead to those kind of large differences with every single cycle, large changes in electrostatic enthalpy that we can then harvest in the form of electricity, okay? So that's kind of one advantage of dealing with the nonlinear model. The second advantage of dealing with the nonlinear model is we can actually kind of play around with this electrostatic loading. So, although the external excitation is harmonic, say sinusoidal, there's no reason to believe that voltage at these capacitors should be supplied in a kind of sinusoidal way. Maybe, a sawtooth function is the best, right, for applying voltage to these capacitors. Maybe a square wave function is the best. Okay, so we kind of want to leave that open, and that introduces additional nonlinearity. Okay, so we can kind of study this and just look at the amplitude of the tip. And when we kind of plug in values and we excite this at resonance, we kind of get the response that we expect. We start seeing, we kind of get the steady state. And this portion of the analysis is fairly consistent with our linearized type models and predictions. I'm going to skip all the derivations of the linear approach and the solutions there. Most important and kind of interesting, though, are the results that we get when we kind of do an optimization and see what is the optimal electrostatic loading. What kind of electric field or voltage do we need to supply to these plates as a function of time in order to harvest the maximum amount of energy? Okay, and what we find, one thing is surprising, the other thing is not surprising. So not so surprising. So when we do, we use like a Fourier series parameterization of that voltage. What we find is that the actual optimal type of electrostatic loading is a square wave. Okay, which is kind of what I illustrated a few slides earlier. So that is not surprising in the sense that it's consistent with kind of our intuition with how energy harvesting works, right? What is kind of a little more surprising though is that there's actually a kind of optimal kind of voltage. If we apply too much voltage, we're actually not going to be generating more electricity out of our system. Okay, and so that's something that this is kind of the solution if we don't factor in the internal Maxwell stresses due to the high voltage that we apply to the capacitors. But here we see that in terms of the energy output, we do have a kind of a very kind of clear optimal kind of applied voltage at which beyond that point, applying any more voltage will basically just cause our vibrating capacitive array to basically just lock up. Okay, so we won't really see enough of that elastic deformation that we need for energy harvesting. Okay, so those are kind of some of the important lessons here that we can get from that nonlinear model. I mean, basically the bottom line is like kind of what I want to kind of communicate is that these, a lot of these kind of principles and then modeling tools in nonlinear elasticity are going to be very important kind of as we kind of more and more enter the space of soft robotics and then we start using these fluids and elastomers that undergo very large elastic deformation. Okay, so that's work with actuators. I kind of want to kind of change gears here, kind of put aside some of that modeling stuff and kind of focus a little bit more at a higher level in terms of different paradigms or approaches to very soft and stretchable circuits for our electronics and sensing. Okay, so a few kind of approaches right now, kind of I'd say probably the most mature are wave electronics. Okay, so I mean you're probably mostly familiar with this from the work out of University of Illinois, Northwestern, introducing stretchability through wavy patterns, buckling, through meshes, serpentine shape. So this is great for achieving kind of stretchable functionality using kind of conventional electronic materials. One disadvantage of this is that you only get stretchability in the directions that you design. Okay, so these are not scalable in the sense that there are length scales, which of course these devices are not stretchable, and they're also not isotropic. Okay, and then kind of the third limitation, and I mean, this I guess depends on kind of the scale of your research program, is that these are can be very challenging to make and to integrate into other soft systems. Okay, if you wanted to scale this up, I mean, eventually you would need like multi-billion-dollar fab labs, for the types of materials that we're using here. But nonetheless, still, I mean, a very kind of I would say at this point, fairly kind of mature approach to dealing with stretchable electronics. Kind of even more mature, of course, is to use conductive elastomers, as we talked about. So these are intrinsically elastic, but they suffer from very low conductivity. And in fact, a lot of times, at least with commercial conductive elastomers, they wouldn't even be marketed as conductive elastomers. They would be more kind of marketed as just anti-static type materials. Okay, so for us, kind of one material that we found to be kind of very versatile and kind of a very good compromise between these approaches is to use metals that are liquid at room temperature. Okay, and I call these liquid phase electronics. Basically, we're taking liquid metal alloys and then we're putting microfluidic channels of those and bending them, sealing them into rubber. Okay, so just as conductive as conventional metal wiring, but they're in fluidic state, right? So they kind of are, I mean, they can kind of stretch with the surrounding elastomer matrix. And I mean, in terms of volumetric conductivity, I mean, you can see how, liquid phase metal alloys like Gallium-Indium are kind of much more closer to conventional metal wiring or wiring than they are to conductive elastomers out there. Okay, and here's just kind of an example of taking a microfluidic channel of this liquid metal alloy, putting in rubber, and you see even as you stretch it, that microfluidic channel remains intact. Okay, and that's great because that's kind of one mode of very highly stretchable circuit wiring. By stretchable, I mean like as stretchable as the surrounding rubber. So it could be as much as like 5, 10. You could stretch almost to 10 times, say, the natural length of your circuit. Another kind of thing, kind of interesting feature is that we have very strong electromechanical coupling, as you saw with that dielectric elastomer actuator. In this case, if we apply, say, some surface traction, we apply pressure, we stretch, we bend these materials. That's going to change some of the circuit properties of those embedded liquid metal channels. Okay, so one coupling between elastic electric resistance. And this is by did this is at a conference last year. Basically made a capacitor array embedded in a soft, and you see that there's a elastic deformation in this case with Okay, so the way I kind of arrived at the site electric resistance was almost by accident. I mean, I was originally trying to create some type of electromechanical, or creating some kind of liquid metal channels. If you just had a little bit of pride on these channels, that was enough shut, collapse, and you could have some kind of opened and closed channel. But then when I kind of just wanted to start applying pressure with connectivity, you have extreme amount of pressure. Okay, like if you can tell, let's apply up to say like 100 pascals, resistance shoot up, and you lose. And 125 kilopascals modulus of the speaking, we're talking very high. It occurred to me that, you know, maybe not ideal as an electric, but sensor, right? So I kind of will pressure sense two of these microchannels and put them inside this elastomer as you push down the electric. Kind of nice about this is use this kind of inelasticity, 3D linear elastic fracture mechanics with a coupling and relative change in electric. Here as we treat once a crack, and just like in fracture mechanics, it opens. Kind of if you apply pressure, the crack. In fracture mechanics, we have a mapping between that kind of and that change of that channel, and then we take that, and that's kind of proportional area of the channel. We area of the channel, plug that into Ohm's law. Electric resistance is that predictions we made with our experimental measure fitting here, and we're not, you know, everything we're using. I mean, all the, you know, we weren't getting good agreement with these classical solutions. What's important here is that we can take these methods and come up with design principles that can inform what is that our pressure sent to a certain range of pressure, useful value that comes out of pressure. Okay, almost kind of like a threshold, you know, below which we can. Okay, and that tells us, you know, what the function of Young's modulus in the channel are useful. Say if you want to say keypad, where we know that pressure kilopascal is intrinsic, that will kind of inform us that versus something, right, where the pressure is, you know, we can refer back to theory, okay, our characteristic values in order to kind of appropriate materials that might work now. So we could different types of resistive pressures. We can also, you know, experimentally validated capacitance, use changes in, and generally what we'll do is, you know, fairly good agreement in theory and experiments. I kind of want, instead what I want to do is just wrap on how we actually make these. As helpful as those are, as helpful as just to know that, you know, we can use all these things. I mean, today, like one of the big barriers of building soft stretchable circuits are limited fabrication. Effort from the pastor and developed using rapid protocols, staying out of the clean room. You know, how are there ways that we, you know, within a few hours we liquid metal alloys with insulating elastomers being functional. This was really at NC State University. It was before at Harvard, and when I was adopting this of embedding these conductive Gallium-Indium getting stretchable electronics. Initially, that work was done so kind of it's very reliable, but you are geometries you can make. I mean, you can only, you know, you're limited to a single inlet, single, you know, it's very circuit features with and to make 3D type. So kind of one alternative sensible lithography, and this is something that we can scale, micro scale, and so we had on that, and you know, kind of sensible lithography approach. Published last year was on this technique where the advantage of the fact that it was liquid at room temperature, built some cold chamber, cast, and pretty much like you would any conventional metal, that, you know, take it out, you know, handle this in this kind of pieces together, and then just bring it back encapsulated, just kind of melt. Okay, so this is kind of one kind of with kind of more like you know, rigid uses, you know, to make assemble a structure so that I can go back to this thing. So that was kind of a lot of our focus on like micro contact printing or stand, also laser patterning, kind of conductive elastic. Yeah, you can make spin coat elastomer and just take a CO2 laser. You can kind of, you know, make and flexible circuits. You didn't really know yet is if you could alloy. Why this is important is simultaneously with your conductive elastomer, then you could make these integrated and with. That was fairly straightforward. I mean, you know, insulating conductive aluminum plate with a CO2 6 micron wavelength plate. Okay, with a UV regime, right? Because as with any metal under UV, it kind of surprised people when we were able to laser the pattern. Only able to when the liquid between two layers of PDMS was that PDMS and basically creating a vapor blast away, vapor recoil force away all the produce pattern. Okay? We were going to do a method. Using kind of one to simultaneously patterning is like immediate electrical kind of manual steps, you know, functional, and we have in this case like a cPDMS with our liquid metal, some LED. Kind of working, and this is still in terms of and kind of allowed is to use principle here is It's fairly kind of treat that we can dip in a stamp or patterns to another. So here's this like a single dip into a pool of our, and using the Cartesian droplet to the surface, and then we can deposit the droplets close enough, form lines, and then freeze this and seal it up. So that's kind of one approach. Originally, it worked at kind of the we're currently looking at this. Okay, and so we've had with using this printing technique now, pattern liquid metal, and then down to the submicron. Get liquid metal using planar dimensions. Just a few hundred. And what's also cool about the actuators and a lot of the same kind of in theories at this smaller length scale. Okay? You go do say theory testing capacitance that are almost identical as well from theories out there for say cone. So that kind of also gives in at this kind of smaller length still have a lot of success. That's cool kind of conventional approach. I think but prospects and lessons of different approaches to in soft robotics have their pros and cons. Non-dielectric elastomers, but that theory really is kind of informed the design to make in terms of solid pneumatics, shape change. You also get reverse. Very important when you want to perform. And so that's kind of remains with our lab. Kind of analogies in nature, including your natural working on the synthetic. Again, I mean, there's all sorts of capacitive, and that's another kind of domain where good predictive modeling with informing design, fabrication, and then this is going, right? I mean, ideally, with high volume technique where say you integrate all these materials, automated, kind of a very rich space. I mean, and again, I mean, just kind of in this theme of soft matter engineering, kind of see this as being multi-lab, multi-university. So, and I really do kind of the soft machines lab just from one very space here, from this. To see how we can kind of complement what you guys kind of achieve the kind of business needs for us in the form of artificial skin tissue. So with that, I'd like thank you.
Other questions for our speaker?
I guess my question trouble with sometimes using your soft.
Yes, we have a vision, and that's something that is I didn't want to preliminary work to you guys come up with some techniques. This is a different kind of material. I've been figuring out, how that. I would say generally just have a direct link between rigid material, right? Be of reasons, okay, but concentrations would. So what we do is ways, and then to some that one, and then the silver PDMS. Yeah, I mean this one like this LED with kind of that makes PDMS, and then the silver PDMS. So you need some level of gradient, so it's mechanical impedance mismatch for rigid materials. The materials out there, but again, I mean, they have very low conductivity. I mean, once when you kind of as these you do get a lot of that could alter the performance.
Your actuators, and you picked two different modes. One was extensional. You thought about trying to have actuation be the same, get regenerative.
I have not thought about that. I mean, so one of like the challenges with using electrostatics or dielectric elastomer actuators for energy harvesting is that regardless of whether you're in compression or extension, when you apply that charge, it's always going to be compressive, right? So I don't know if you actually look back at it's probably easier if I just pull it up this way. Probably the sketch will be the best. So it's kind of like a square wave type voltage that you have to apply. But basically the square wave is kind of offset. So basically you're going between 0 volts and then some, say, hundreds of volts or kilovolt. But, and so when you're under compression, you don't want to apply any voltage. So basically you're only harvesting energy like half the time during your excitation. The problem is that if you try to actually do like a square wave where you have, say, like negative voltage, it would still apply compressive stress during compression, so you get basically going from energy harvesting to amplification, and basically the two would kind of cancel each other out. And so you would get like no net output of energy, of electricity.
When you laser pattern your EGaln, what prevents it from flowing out of the channels? Is it frozen?
It's the service tension.
Service tension.
So, and in fact, I wouldn't even say it's service tension. It's so what happens is, I didn't talk about this, but you could kind of see it in this picture here. So I'll just kind of point it out to you. The liquid metal forms this gallium oxide skin, and that allows it to hold its shape. So that's the other kind of essential, that's the essential property where kind of liquid metal is kind of unique in being able to be laser patternable using that vapor recoil force from the PDMS because of this gallium oxide skin that it forms. It basically holds the liquid in place inside the channels. It basically prevents it from kind of spilling out. Yes.
So how strong is that skin? Like, how much can you kind of stretch them? Something that's only being held in?
Right. It's incredibly. It's pretty impressive. I mean, I don't have a good number in terms of what the fracture strength of the gallium oxide is. I mean, I would expect it to be on the order of oxide. I mean, like that. I would expect it to be on the order of hundreds of megapascals. I mean, and the one issue though is, I mean, so, a lot higher than any kind of hydrostatic pressure can be building in the liquid underneath. So it's certainly enough to kind of allow these droplets to hold their shape at least under gravitational type loading or under kind of normal pressure. The skin though is very thin. I mean, we're talking 5 angstroms. I mean, measurements are on the order of about 5 angstroms to maybe 1 to 2 nanometers. But yeah, they're incredibly strong. I don't have the exact number for you though. But that's actually something that Mike Dickey has actually looked at. He hasn't published that work yet, but he's kind of done kind of a series of tests to kind of better characterize mechanical properties of that gallium oxide skin.
Does that skin help reduce some of the corrosive properties of working with this?
No, it helps in the sense that it's basically the product of the corrosive properties and it's self-passivating. I mean, if you don't want to get it on your skin, I mean, because it will, or in organs or tissue or whatever, just because it will corrode. I mean, if you put a droplet on like a Coke can, it'll eat right through. I mean, it's incredibly corrosive, especially against aluminum for some reason.
I guess the follow-up would be, are there other types of materials you're considering for soft robotics applications that aren't as corrosive if there were to be, a break in the elastomer that's holding the vehicle?
Yes, I mean, there are some that we're exploring. I mean, I don't want to be too speculative, so I don't want to throw stuff out there that we haven't carefully explored. I mean, but yeah, there are other directions that we're looking at. But yeah, I mean, in terms of, this is not toxic, but yeah, in terms of looking for passing FDA approval, then, I mean, right now, the only thing that we know for sure would be say, carbon filled PDMS or something. That's completely biocompatible. We still have to we haven't actually done yet, we're planning to do this toxicity tests with the liquid metal using live cells to see how they stand up. Yeah, but yeah, the oxide could, in principle, I mean, if you don't rupture it, I guess could help prevent against corrosion, and also if you had, and this is another kind of recent study by Mike Dickey, is also, there are kind of ways that you can kind of create like a kind of boundary layer around it to prevent kind of rupture and contact with the gallium. Yeah.
I have a question about the possibility to design distributed sensor using
Okay.
liquid or using other
Right.
material. Is it feasible?
It is feasible, but kind of one challenge, and I mean, I think you guys will have better ideas than I do. I mean, this is even something that, starting with Professor Bergweder, came up is, with these, when we're talking about, especially with these kind of miniaturized type electronics, where you have hundreds of thousands of these nodes, you do, ultimately, if you're doing resistive or capacitive sensing, you're going to have that electrical beads, to all these nodes. You have all these terminal points, and then you have to do some level of multiplexing at some level to connect that to, through an 8-channel or 16-channel, bit channel to your processor. So yes, having more sensors means more multiplexing, unless kind of locally, you can do some type of processing, deal with that in some ways. But those are mechanisms that I don't know about. I'm not the electronics guy in that regard.
Okay, I think at this point we better stop and thank our speaker again.